yes, we can see your screen there. It should still be recording, I believe. Yep, still recording, so you should be good to go when you're ready.
Okay, and I hope you hear me.
Yes.
So, silicate liquid immiscibility in late intrusions was first found in Skaergård. This is Wager and Brown Symposium, after all. So, Skaergård is a place where almost everything has been found for the first time. So, it was discovered by Alexander McBurney more than 50 years ago in Skaergård. And then basically for many decades, I would say up till now, it is still more or less ignored and considered to be a late stage phenomenon with little petrologic importance. But I'm happy that Marian Holness already introduced you into this potential of liquid immiscibility in Skaergård and some possibly undiscovered consequences of this process in late intrusions. So this is the paper by Jacobsen et al. 2005. That's about time when I got personally involved in liquid immiscibility. And we did, after that, I got very excited because basically, to me, it was like a reconciliation and the final solution for the old Fenner versus Bowen controversy about the general trend of melt evolution in Skaergård. So basically, it shows that magma produces both iron-rich and silica liquids at a certain evolved stage of magma evolution. And we did a bunch of experiments. This is not my experiment. We did experiments in a centrifuge at high temperature, specifically to try to distinguish between quench and stable liquid immiscibility. We produced emulsions, which were controversial and which were subjected to long debates. And we tried all we could to sort of prove that actually emulsions existed at high temperature, but looks like people still don't believe that. The more conventional experiments are illustrated here. This is a paper from 2012 by Bernard Chalier and Tim Grove. They have taken natural rock, that natural volcanic rock with immiscible droplets of iron-rich liquid in silicate glass. And you see these liquids are multiply saturated in plagioclase, in magnetite, and in clinopyroxene. And they heated it up, remelted it, and observed the disappearance of immiscible globules. So based on these experiments, most people believe that immiscibility in thalitic basalts, in common basaltic magmas, actually doesn't exist above 1040 degrees centigrade. So basically, I'm not so sure. I haven't been so sure. And Alex Borisov and I decided that it would be nice to check chemical equilibrium and to get some insight into this complicated processes of liquid immiscibility on multi-component systems, if we have some kind of chemical indicator whether liquids in experiments and in natural samples are actually in chemical equilibrium. And as you know, oh yeah, and I also should mention that why I am not sure that liquid immiscibility actually starts at below 1040 degrees C is I think I have serious reasons for these doubts, because this is a recent paper by Honore and others, and they looked at samples coming from the drilling project when the Kilauea lava lake was drilled. It's kind of instant quenching, And at 1112 degrees C, you see these plagioclase crystals, and these are surrounded by a layer of immiscible iron-rich liquid that nucleated in this growth zones around plagioclase, and silica-rich liquid nucleated around clinopyroxene crystals. So this is a very nice illustration of the complex interplay between crystallization and liquid immiscibility. In this case, crystallization and boundary layers formed around crystals, they kind of help to nucleate the second, the immiscible liquids. But I would, later in the talk, I will show that sometimes it's just the opposite, that crystallization competes with liquid immiscibility and hampers separation and nucleation of the second liquid. So the idea is to find some kind of a chemical indication to check equilibrium in experiments. Like we check equilibrium between olivine and basaltic melt by looking at Mg numbers and looking at Kd iron magnesium, which is 0.3, as everybody knows, and it works reasonably well with very little exception. So what elements to choose? We need a reasonably complex system, not a binary with liquid immiscibility. We need reasonable number of components to approach natural compositions later on. So the most experimental coverage is for this 5-oxide system, potassium, iron oxides, alumina, silica. This system first studied by Roeder, then was studied by many other people at different oxygen fugacity, at different pressures. And as you can see, liquid immiscibility covers quite a range of temperatures, all the way to above 1450 centigrade. This is an example from Dick Naslund, 1976, different oxygen fugacities and different topology of the system. So there is a significant body of experimental data exists for this 5-oxide system. And choosing potassium and iron is also kind of has also, makes lots of sense, because potassium strongly concentrates in the silica-rich liquid, and iron is basically essential component of the iron-rich liquid, the indicative component of the iron-rich liquid. So they're contrastingly distributed, and their distribution should be very sensitive to equilibrium. So the reasons are good experimental coverage and very contrasting. So lots of data for the partitioning of these two elements, and they're very contrasting distribution between two liquids. So what we did first, we looked at, we collected this data, and we collected about 200 pairs of analyzed immiscible liquids. And we tried to just, we tried to look at the Nernst partition coefficients for iron and for potassium. So for iron, and this is the upper plot, we see that actually there is a good correspondence between iron partitioning and the contrast in the silica content, which is between the liquids, which is plotted at the horizontal axis. So you would expect that network modifiers like iron and potassium and network formers, and the main of them is silica, they should somehow, there should be some correspondence in their distribution. And that's what we actually see this with iron, although iron is actually two different elements, is iron 3+ and iron 2+. that are quite different in their chemical role and in their structural position in silicate melts, but still we have quite good correspondence between, silica distribution expressed as the difference in concentrations and the ratio of iron content into liquids. But it doesn't work for potassium. Actually, it does work for compositions without phosphorus or with low phosphorus contents. And I should have mentioned that this 5-component system was also studied with all kinds of different additional components like calcium, magnesium, phosphorus, fluorine. So we combined all this data, not only five components, but also more complicated compositions. And we saw that with high phosphorus contents in starting liquids, actually these Nernst partition coefficient doesn't follow any kind of curved or linear trend in these coordinates. And that makes sense because potassium is in terms of the acid-base theory is a strong base, and phosphorus is strong acid. So you would expect strong chemical interaction between potassium and phosphorus, and that's what probably we see in this case. So next idea was to try to make some kind of distribution constant, similar to iron magnesium distribution constant between olivine and melt, and to combine partition coefficients of potassium and iron into this Kd, like the upper formula, and try to somehow to look how it is related to the distribution of other components between the liquid and primarily silica and other network modifying components. So my colleague Alex Borisov, it was mostly his achievement. He used thermodynamic analysis. He looked at the symmetric radial solution models, and actually he found that this expression of Kd has another advantage, that in terms of regular solution model, it can be connected to this is the lower formula. It can be expressed as a function of reverse temperature. This is the first term. Then the sum of the differences in molar ratios of other components in the system, excluding iron and potassium that form a separate term, and then the free term. So this is the kind of the general form of the equation that follows from the regular solution model. After finding that, we used regression analysis. We used multiple linear regression on this experimental database of 195 conjugate liquid pairs. And we tried by trial and error to remove different components and without losing accuracy of the equation. And basically, we came to the result that it is enough to consider, apart from potassium and iron, it is enough to consider silica, alumina, and phosphorus. And then that makes perfect chemical sense, because these are network formers and the main network formers in the natural magmatic system. And by this multiple linear regression, we actually calibrated the equation, and we found these coefficients, which are shown here in this equation. So we were actually able to rid of the temperature term. It turned out to be not very significant, and we have equation with the temperature term and without it. But the advantage of equation without temperature term is that it can be applied to magmatic rocks when we don't know the exact temperature of crystallization, or the temperature of crystallization can be not fixed exactly to some kind of one single number. Free term is theoretically it should be 0, but we kept you know, it just it's not very big number, as you can see. But the reason for that is better accuracy of the equation, and it kind of accumulates all the uncertainty of our analysis. And also, you should keep in mind that experiments and analytical analysis are not perfect. So there is some kind of error in electron microprobe analysis and in experimental setup. And that free term basically accumulates and so absorbs kind of potential errors of all these imperfect procedures. So we got this equation, and this is a test for equilibrium. What kind of test is that? Basically, according to this equation, if liquids are in equilibrium, then you should expect that distribution of network formers, potassium and iron, should be in some kind of correspondence to distribution of the network formers, silica, alumina, and phosphorus, if they are present in the starting compositions. So now we are ready to apply this equation to the experimental products which were not included into the calibration. But first, I should show you. I already told you that it's pretty good. It's pretty good calibration, but I just want to illustrate this by these plots, where I show that with the very big temperature range, different pressures from from atmospheric to 15 kilobars, different oxygen fugacities, and with or without other additional components such as calcium, magnesium, or fluorine. Basically, the equation works, and it actually fits very nicely. You know, statistically quite significant. Now let's see what happens if we apply this test to other experiments which are not included into calibration. And first, there's centrifuge experiments that I have been doing with my colleagues in Munich for several years, and which were debated whether they are quench solutions or they are actually real high temperature emulsions that we managed to separate in a centrifuge. It turns out that these compositions from those from those studies in centrifuge, they actually passed the test quite well, with exception of the few points which were basically reversal experiments. Also note that they tend to deviate to the right. By KD expected and KD measured, I mean that KD measured is directly calculated from the concentrations of iron and potassium measured in the coexisting liquids, and expected are based on the equation and are based on the distribution of silica, alumina, and phosphorus, if they all exist in the composition study. So this is the test, the compliance with the distribution of network formers and network modifiers. That's what we are testing. And now we look at these experiments on multiply saturated liquid with high proportions of crystals. And it turns out that it's not very bad, but actually there is a tendency for the experimental points to shift to the right or below the 1-to-1 correspondence line. And if we look at this black black squares, this is the work done by Victoria Honor and co-authors, and they redid some of the experiments on the same composition studied by Chalier and Grove. And actually, these squares represent a time series. So this is experiments that were run at the same composition, same conditions, but at different exposures. And exposures were up to 300 hours, which is basically the limit of any reasonable exposure time in experimental petrology. And what we see here, and this is highlighted by this pink arrow, that with the increasing time of exposure, we are getting more and more contrasting distribution of the components between two liquids, and that makes sense because diffusion takes time. So you need hundreds of hours to sort of reach some kind of better separation and better transport by diffusion, but the direction of this, so these points, they kind of follow a trend with a shallower slope. And what it means that network forming components, silica, aluminum, and phosphorus, they are not exactly coping with the distribution of they are not exactly matching the distribution of potassium and iron. And my explanation to that is this is effect of crystals. This is effect of plagioclase, which is basically in a very close contact with the liquids. It's in these experiments on the millimeter scale samples, you cannot separate crystals from the liquids, so they are basically touching and they are within kind of micron millimeter scale distances from each other. And what happens is that for the slow diffusing components of the silica-rich liquid, it is easier for these components to crystallize in plagioclase, to form albite-rich zones on the plagioclase crystals than to redistribute themselves between iron-rich and silica-rich conjugate compositions. So all the points tend to shift to the right. And this is exactly, the direction that I tried to explain. And when we look at the original natural lavas, where basically nobody cared about reaching liquid immiscibility, and they were crystallizing in nature and under uncontrolled conditions. So basically, we see very strong disequilibrium. So these droplets of iron-rich liquid in interstitial spaces in natural basaltic lavas, which were studied by Tony Philpotts and many other people since 1970s, 1980s, they all basically shift to the same direction as the experimental liquids, but to a much greater degree, again, because nobody kept them at controlled conditions for any reasonable period of time. So they are on, and the reason is the same because we have plagioclase crystals nearby. So my conclusion is that equilibrium test confirms strong kinetic competition between crystallization and silicate liquid immiscibility. And the experiments on small millimeter-sized samples with high volume fractions of crystals tend to imprecisely reproduce equilibrium liquid compositions because of this competition. Immiscible liquid droplets in volcanic rocks are often even more in disequilibrium and tend to evolve along with a stable time. And so if we basically have now serious doubts in the experiments on these multiply separated liquids and cannot take examples from volcanic rocks at the the final ultimate truth, I would say that the extent of petrogenetic role of silicate liquid immiscibility, including the question when it actually starts in Skaergård and in other plutonic systems, deserve a revision. Thank you very much.
Thank you very much, Ilya. I guess we are becoming a little bit under the clock, because I think Wolfgang is worried that we have to leave here in an hour.
Yeah, well, we can skip the questions because I'm not with you,
So
unfortunately.
we can have one or two short questions for Ilya. John has a short question.
Ilya, the strange thing about those results is that the valence of iron makes absolutely no difference. You treat iron as iron total, to avoid it. Can you hear me?
Yes, I hear you.
So why doesn't the valence state of iron make any difference at all? Ferric and ferrous are like two completely different elements.
Yes, I agree with you, and I expected that ferrous and ferric iron would have quite different partition coefficients, and oxygen fugassity would play a major role. I'm not quite sure what compensates the difference in their chemical properties. I'm not quite sure, but that's what we get. That makes our life easier, but that's really surprising. I agree with you.
But Borisov knows full well how the ferric-ferrous ratio changes as a function of melt chemistry and temperature. Why don't
Yes.
you calculate for each experiment what the ferric and the ferrous is, and see what K over Fe2 plus as opposed to K over Fe3 plus looks like, and parameterize that?
Yeah. Well, we did calculate the ferrous ferric when we had oxygen when we have information about oxygen fugassity. So we used the equations that he himself calibrated and other people. So yes, the ferrous ferric changes dramatically in the data set that we studied and then tested. One possibility is that iron 3 plus may be less compatible with silicate network, but on the other hand, being an amphoteric component, it's not so much interacted with phosphorus, aluminum, and silica. That could be the answer. So that's kind of two compensating effects. That's the only thing that I can suggest right now.
Okay, thanks.
Yes.
That has been super quick.
Real quick, I did some experiments. The ferrous ferric ratio is different in the two liquids.
Yeah, we don't know if ferrous ferric in two coexisting liquid is different. I don't know. I don't know.
Okay. Thank you very much,
Okay,
Ilya.
I'll move quickly.
Okay, so Wolfgang says now that we have until 6 o'clock.
We have until 6 o'clock. So for Steve and Alan, I think it's enough time with a few questions. Huh?
Okay.
1.5 hours. The session we will have to do tomorrow then. Tomorrow we have prompts for